This video is about derivatives of specific inverse functions, such as natural log of x and inverse trig functions, and also general inverse functions. We start with some specific ones. Use the chain rule, not the definition of the derivative, thankfully, to find the derivatives of the following functions, which are inverse functions of special functions you should know. Part A, f of x is natural log of x for x greater than 0. You should know, I'm assuming you know, that that's the inverse function of e to the x. We will make use of that. But there is a big question. How in the world do you make use of it? Part of the hint is the chain rule. Part of the hint here that I'm giving you right now is the fact that this is the inverse function of e to the x. We know because of that, that e to the natural log of x power equals x for all x in the domain of natural log of x, which is all positive x. For all positive x. What can you do with this? You could try differentiating both sides, but if you're pretending you don't know the derivative of natural log of x, how could you do that? You could still write it symbolically. That's the key. This is the composition of two functions. The inside function is natural log of x. That's what gets done first. The outside function is e to the x. We know by the chain rule, let's go ahead and differentiate this, that you take the derivative of the outside function, which is e to the x. Its derivative is e to the x, but then plug in the inside function and then multiply times the derivative of the inside function, which we don't know. We're pretending we don't know at least. Just write it symbolically as d dx, the derivative with respect to x of this function, natural log of x. If we differentiate the left side, we've got to differentiate the right side. The derivative of x is 1. In writing this, we are assuming the derivative of natural log exists. That's why this is not a proof, but we're trying to just derive or find that derivative, assuming it exists. And this is now an algebra equation. We can solve for that unknown derivative. Just divide both sides by e to the natural log of x. This implies that the derivative we seek, the derivative with respect to x of natural log of x, is 1 over x in the domain of natural log of x. This is for all x that are positive. Okay, this is a fundamental fact to know in calculus. Let me do a little bonus here that is not being asked for in this question. Let's also find the derivative with respect to x of the natural log of negative x for x negative, so that negative x, the opposite of x, is positive, using what we just found and using the chain rule. This is a composition. The inside function is negative x, the outside function is natural log of x. The chain rule says take the derivative of the outside function, natural log of x, to get 1 over x, but then plug in the inside function, so replace x with negative x, then multiply times the derivative of that inside function. The derivative of negative x is negative 1. Those two negative signs will cancel, giving you 1 over x. This is true for all x less than 0. Hey, it's the same answer. Isn't that amazing? Maybe we could put these two things together. Yes, we can. We can put these two facts together to say that in general, the derivative with respect to x of natural log of, what should I use? What quantity will equal x when x is positive and negative x when x is negative? You should know it's the absolute value of x that will be what equals x when x is positive and negative x when x is negative. Negative x is a positive number when x is negative. It's got to be the same answer when x is positive or when x is negative, but not when x is 0. This is true for all x not equal to 0, and that's also a fundamental fact to know in calculus that is useful for integration. All right, let's do part B now. Part B says the function is inverse sine of x, also called arcsine of x. You should realize those are two names for the exact same function. And you should also realize that this is not the same as 1 divided by sine of x, because 1 divided by sine of x has a different name. It's called cosecant of x. It's not the same. Cosecant of x is the reciprocal of sine, the multiplicative inverse. This is a inverse function, which I will briefly talk about graphically after I derive the answer here. So how do you do this? It's the same kind of method. We know that sine and inverse sine are inverse functions of each other. I can write sine of inverse sine of x equals x for all x in the domain of inverse sine of x. which you may or may not know. This is true for all x that are between -1 and 1. That is the domain of inverse sine. Now I'm going to do the same method that I did to derive the derivative of natural log of x. I'm going to differentiate both sides. And in doing so, again, I'm assuming that the derivative of inverse sine of x exists. However, I will tell you ahead of time that assumption actually is faulty at the endpoints of the interval. And when we see the final formula, we will also confirm, yeah, that final formula can't possibly work at the endpoints. So take the derivative with respect to x of the left side, use the chain rule. The derivative of the outside function, sine, is cosine. So we get cosine, we got to plug in the inside function into that, cosine of inverse sine of x, times the derivative that we seek, the derivative with respect to x of inverse sine of x. And that all has to equal the derivative of the right side, which is, again, 1. So we could write the derivative with respect to x of inverse sine of x as, divide both sides by this expression right there to cancel it on the left, 1 over cosine of inverse sine of x. And I mean, you can see here that you can't include the endpoints if you're careful in thinking about this. If you plug in x equals plus or minus 1 here, inverse sine of 1 is pi over 2. Inverse sine of -1 is negative pi over 2. Cosine of pi over 2 or negative pi over 2 is 0. We would be dividing by 0 at the endpoints. This is for all x not between -1 and 1, but not equal to 1. However, I will also say, though, that this is not the way we usually write the final answer. This answer involves trig functions. You can actually write the answer without trig functions, amazingly. How? Well, we can use the Pythagorean identity, for one thing, to write cosine of inverse sine. Okay, what does the Pythagorean identity say? It says cos squared theta plus sine squared theta always equals 1, no matter what theta is. You can solve such a thing for the cosine. And assuming we take the positive square root, that's an assumption that may be faulty, but let's go ahead and do it here anyway. We can write cosine of something as square root of 1 minus sine of that same something. Okay. Actually, here's a brief justification for why we can take the positive square root. Inverse sine of x will give you an output between negative pi over 2 and positive pi over 2. First or fourth quadrant, if you want to think that way. The cosine of such an angle is positive. We can take the positive square root. And this, oh, I forgot something. This needs to be squared. You could put the square here as well. That's just notation. And then sine of inverse sine of x is x. There we go. This is true for all x strictly between -1 and 1, and that is the more common way to write the answer for the derivative with respect to x of inverse sine of x. Graphically, what's going on? This is worth thinking about briefly. I'll go ahead and graph 3 functions here. The sine function, the inverse sine function, and let's graph the derivative of the inverse sine function, 1 over the square root of 1 minus x squared. Okay, we'll graph these in the same window. When x is between, okay, I'm going to make a bigger window than the domain of the inverse sine function. Hopefully we won't get an error. Let's go -2 to 2. And we may need to, actually I want to graph another function in here. I think let's graph y equals x in here as well, to hopefully see the reflection property of the graphs of sine of x and inverse sine of x. I'll pick a window -2 to 2, but we may need to use the zoom square to make it look square so the picture looks better here. Okay, so the first graph is the graph of sine. It's not 1 to 1 overall. We have to restrict its domain to make it 1 to 1. There's the graph of inverse sine. There's the graph of the derivative of inverse sine, and there's the line of y equals x. And let's see if we can do a zoom square, z square here, to zoom in so that we see the reflection property More clearly, there's sine, there's inverse sine, there's the derivative of inverse sine, and there's the y equals x. And what I wanted to point out by drawing y equals x is the graph of inverse sine of x is the reflection of the graph of sine of x across that line when you restrict the domain of sine of x to being from negative pi over 2 to positive pi over 2. This piece of the sine graph right there gets reflected across that line to give you the graph of inverse sine. And the derivative of inverse sine, it's no proof, but it's reasonable that it looks like this, because the graph of inverse sine is always got a positive slope, so its derivative always has to have positive values. The minimum slope occurs at x equals 0, just like that derivative has a minimum at x equals 0. And what's happening as you approach plus or minus 1? It turns out the slope of the tangent of the inverse sine as you approach plus 1 or as you approach minus 1 is going off to infinity. This graph has a vertical asymptote at plus or minus 1, which makes sense if you look at its formula. All right, let's go more quick with the next few parts. Part C says find the derivative of inverse tangent, also called the arctangent function. Same kind of deal here. This is part C. Tangent of inverse tangent of x equals x. This is true actually for all x, because it turns out the inverse tangent function has a domain that is all x, okay? This is true for all x, amazingly. Do the same kind of thing. Take the derivative of both sides. In the last video about derivatives of trig functions, we saw the derivative of tangent is secant squared. Plug in the inside function, then multiply times the derivative of that inside function. Differentiate the right side. Solve for the unknown derivative, d dx of, oops, that's supposed to be an x, of inverse tangent of x. Could be written as 1 over secant squared of inverse tangent of x, and that would be true for all x. That's part of the domain. Does the secant of that ever equals 0? Secant is 1 over cosine, and that would never equal 0. 1 over cosine is undefined in places, but it's not going to be undefined for any x here, because the inverse tangent of x will never equal plus or minus 1. So the cosine of that would never be 0. You'd never be dividing by 0 here. This is true for all x. But once again, it's not the way we typically write the answer. Again, you've got the fact that cos squared theta plus sine squared theta always equals 1. That's the Pythagorean identity. If you divide this equation by cos squared theta, it becomes 1 plus tangent squared theta equals secant squared theta. So this secant squared of inverse tangent of x can be rewritten as this, 1 plus tangent squared of inverse tangent of x. But remember, tangent squared of something really is tangent of that same something quantity squared. So we take the tangent of inverse tangent of x and square that. But the tangent of inverse tangent of x is x. That equation right there. So this simplifies to 1 over 1 plus x squared, and that's true for all x. Without me using my calculator, quick graph. The graph of inverse tangent turns out to look about like this, and the graph of its derivative is a bell-shaped kind of curve. It's not the true bell curve in the usual sense, because that's related to exponentials, but it is bell-shaped. I may not have the vertical axes here correct. Let's see, the green graph goes to pi over 2, and this graph goes up to 1. So this graph, this bell curve, goes a little lower, actually. It doesn't quite go as high as the green graph goes. All right, let's go on to part D. Find the derivative of inverse cosine of x, also called arccosine of x. Again, I'll go fast here. It's going to be pretty similar to part B. Let's use red here. It's going to be pretty similar to this one. Maybe for the sake of time, because this is getting long already, this problem, let me just talk about the changes you would make. If this were dealing with inverse cosine, I'd have a cosine there and an inverse cosine of x there, equaling x for all x between -1 and 1. If I took the derivative of that, it would become negative sine, right? The derivative of cosine is negative sine of, plug in the inside function, inverse cosine of x, times the derivative with respect to x of inverse cosine of x, equaling 1, We'd solve for the derivative of inverse cosine of x. That would go right there. We'd get 1 over this, which has a negative sign. We can bring the negative sign up in front. We'd get negative 1 over sine of inverse cosine of x. A negative sign in front would be there. And it turns out you'd get negative of this kind of thing, except with a cosine and an inverse cosine, or with a cosine and an inverse cosine there. You would still get 1 over square root of 1 minus x squared when you simplify here, but with a negative sign in front. You would ultimately get negative 1 over square root of 1 minus x squared. Weird. The opposite of the derivative of inverse sine. Part E. What do your answers to B and D for the derivatives of inverse sine and inverse cosine imply about the relationship between inverse sine and inverse cosine? What we've just found, very quickly here, with the derivative of inverse cosine, is that its derivative is the opposite of the derivative of inverse sine. So that would mean, I'm going down to part E here, for example, that if we differentiated the sum of inverse sine and inverse cosine, that we would get 1 over square root of 1 minus x squared plus negative 1 over square root of 1 minus x squared. In other words, minus 1 over square root of 1 minus x squared, which is always equal to 0 for all x. And what would that mean? Got a function whose derivative is always 0. There's something called the constant function theorem. That means this function must be constant. Inverse sine of x plus inverse cosine of x is a constant for all x in the domain, which is negative 1 to 1. Really? The graph of inverse sine we saw was this thing right here. Add this to it, you got to get a constant. What does the graph of inverse cosine look like? Let's add that to the picture, although it's going to go off the screen a little bit if I do it. Let's go ahead and do it here anyway. Inverse cosine of x. There it is. It's the reflection of the inverse sine graph across a line, a horizontal line right here. Where is that horizontal line? I'm forgetting offhand. It could be at pi over something. I'm forgetting where it is. Okay, I should probably know that. But if you then graph their sum, you will get a constant function. This is up at pi over 2. This is pi over 4 there, about 0.7 something. Okay, yeah, that seems reasonable. This constant is pi over 2. In number 2, we take what we learned in number 1 and apply it. Find the derivatives of the following functions that you see. Part A, f of x equals natural log of x squared. Do this one in 2 ways. What could I mean by that? I'll let you think about it. Let's do it in perhaps the most obvious way. Let's use the chain rule. ln of x is the outside function, x squared is the inside function. Take the derivative of the outside function, ln of x. That derivative is 1 over x, like we just found, but then plug in the inside function into that to get 1 over x squared. Then multiply times the derivative of the inside function, 2x. Simplify, you get 2 over x. This would be true, actually, including when x is negative. This is for all x, positive or negative, but not equal to 0. Interesting. This derivative is twice the derivative of the natural log of x. That's kind of strange, you might say, since it's an x squared in there. What would be the second way to do it? How about use a property of logarithms? This would also equal, that's a sideways equal sign, not an 11, the derivative with respect to x, bring that power out in front of 2 times the natural log of x. Hey, yeah, that's another reason why the answer is 2 over x. That's also true for all x not equal to 0. Kind of amazing. All right, part B. Find the derivative with respect to x of this function that you see here. I didn't put an f of x. I could have called it f of x. I just forgot to. Arctangent, which is the same as inverse tangent, of this product e to the 2x times sine of 3x. So we need the derivative of arctangent, we need the chain rule, we need the product rule, we need the chain rule again. This is kind of complicated. What is f prime of x there? Okay, take it step by step. Okay, the most inner function is e to the 2x times sine of 3x. The outside function is arctangent, which is the same as inverse tangent. We just saw in number 1 that the derivative of inverse tangent is 1 over 1 plus x squared. So we get 1 over 1 plus, well, with the chain rule, we have to take this entire inside function and square it. When you square a product, you square each thing individually. E to the 2x squared is e to the 4x. Sine of 3x squared can be written as sine squared 3x. Then multiply times the derivative of that inside function. I'm going to need the product rule as well as the chain rule for that derivative. That's a first function times a second function. Make sure you put the derivative inside parentheses. We're going to take this fraction and multiply times the entire thing here. We could put whatever we get here up in the numerator of the fraction as well and write the answer as one fraction. So we got the first function, e to the 2x, times the derivative of the second. The derivative of sine of 3x will be 3 cos 3x, right? That's the chain rule. Plus the derivative of e to the 2x is 2e to the 2x by the chain rule, times the second function, sine of 3x. There we have it. That's the derivative of the inside function. As I just said, this entire expression could go up into the numerator and write the answer as one fraction as well. Part C, f of x is inverse sine of x divided by inverse cosine of x, which you could also write as arcsine of x divided by arccosine of x. Careful. It's very tempting to think, oh, since tangent is sine divided by cosine, I guess that means inverse tangent is inverse sine divided by inverse cosine? No, no way. It's not true, okay? Don't think too simplistically. That is not true. We'll see, we'll get a different derivative anyway. So let's go ahead and differentiate that. That is a quotient of two functions. I need the quotient rule. It does not equal inverse tangent of x. Need the quotient rule. Low d, I think of it as low d high minus high d low over the square of what's below. Low, inverse cosine of x. D high means the derivative of the top, the high function. The derivative of inverse sine of x is 1 over square root of 1 minus x squared, like we just saw. Low d high minus high inverse sine of x. D low means the derivative of the lower function. The derivative of inverse cosine of x, we also just saw, is this thing with a negative sign in front. So since we get an extra negative there, that cancels with this negative to give a plus. We could write it like this. Over the square of what's below, inverse cosine of x squared, is that like cosine to the negative 2 of x? No, it does not equal that. Write it like this. Inverse cosine of x quantity squared. That's probably the best way to write it. Do not multiply those exponents. That would be not something to do, because this is not a power. It's indicating an inverse function. So it's inconsistent notation, but that's the way that math is sometimes. Could you simplify this? Well, you could combine the fractions up top. You could also write the whole thing as one fraction if you like. That might be worth doing, I guess. You could write it as inverse cosine of x plus inverse sine of x, all divided by this thing, inverse cosine of x quantity squared, and also the thing we divided by on top, square root of 1 minus x squared. Okay? Wow, derivative rules really are amazing. Imagine doing this with limits. No way. Part A of this problem is an abstract version of what we did in number 1. Assuming f of x is differentiable, has a derivative, and invertible for all x, use the chain rule to find the derivative of f inverse of x in terms of f prime. A little hint about how it's going to look, okay? So, how do we do that? Mimic what we did in problem number 1, except we're doing it abstractly. We know f of f inverse of x will equal x for all x in the domain of f inverse of x. Now, does f having a domain that is all x mean f inverse has a domain that's all x? Not necessarily, actually. In fact, if f of x were arctangent, inverse tangent of x, and its inverse function was thought of as the tangent, restricted to the domain of negative pi over 2 to positive pi over 2, it's not true that arctangent of tangent of x equals x for all x. It's only true when x is between negative pi over 2 and positive pi over 2. That's just switching around their roles from what we did in number 1. switching around which one is f and which one is f inverse. So this is true for all x, not overall, but in the domain of f inverse, which we're not specifying what that domain is, but it doesn't have to be all real numbers. As far as deriving the derivative here, use the chain rule. The derivative of the outside function is f prime, but then plug in the inside function, f inverse of x, then multiply times the unknown derivative that we want to solve for, d dx of f inverse of x. Also differentiate the right, 1. Then just solve for the derivative of f inverse of x, d dx of f inverse of x, which we will also write on some problems to come, in fact including part B of this problem, as f inverse prime of x, using prime notation, is 1 over this thing here, 1 over f prime of f inverse of x. Very confusing, very easy to make a mistake, but this is the equation we're after. It's essentially the reciprocal of the derivative of f, except you got to plug in f inverse of x instead of x. Okay, so it's tricky, but it is true. This is what we want. Part B, we're going to use this fact and the graphs that you see below. Use the figure to estimate f inverse prime of 15. So we're going to use this formula. F inverse prime, the derivative of f inverse, evaluated at the input 15, according to this formula, is 1 divided by f prime of f inverse of 15. So we just got to take it step by step. What is f inverse of 15? We got to estimate f inverse of 15 from one of these graphs. I guess it would have to be this graph. This is a little tricky. Usually, I mean, should I try to draw f inverse on here? Should I try to use the reflection across the line y equals x property? Well, that is a little tricky to do, because if you graph y equals x here, the scales on these axes are not the same. The graph y equals x looks like it has a slope of 2, goes about like that, and the reflection property would be tricky because of that. It's not a square zoom box, you might say. So instead of trying to graph f inverse, it's better to think about the graph of f itself and sort of reverse the roles of what's independent variable and what's dependent variable. Usually x is the independent variable and y is the dependent variable. But for plugging in a number for f inverse, you want to think of y as the independent variable. Plug in 15 along the y-axis here, going horizontally first and then down. And you can see the answer is going to be pretty close to 30, maybe slightly bigger than 30, maybe 31, say. Let's go ahead and say this is approximately 1 over f prime of 31. Okay, we also have the graph of f prime. We are treating the x-axis as its independent variable. Yeah, plug in 31, slightly bigger than 30. Looks like we're near a maximum of f prime. In fact, it looks like the maximum does occur at 30. Whether you plug in 30 or 31 to that, the value, the output, is pretty close to about 0.72 or 73. I'll say about 0.73. So this is approximately 1 divided by 0.73. And that will be a little bit bigger than 1. 1 divided by 0.73, that's approximately 1.37. So there is our estimate for the rate of change of f inverse at the input 15. It's about 1.37. Could that be interpreted as a slope? Yes, but sort of in a tricky way here. F prime of 31 is the slope of this tangent line. It's rise over run, delta y over delta x. It's close to 0.73. Doesn't look like it because the scales are off. This derivative, being the reciprocal of that, is sort of like the reciprocal slope, you might say. Instead of change in y over change in x, delta y over delta x, it's delta x over delta y. Right here, you could say delta y over delta x is approximately 0.73, And therefore, 3 dots means therefore, delta x over delta y is approximately 1 divided by 0.73, which is approximately 1.37. So it's kind of like a slope, or it's more like a reciprocal slope, or maybe it's more like a sideways slope if you looked at this picture with your head sideways, maybe backwards looking through a mirror or something. Then you'd see that kind of slope. But again, the scales are different, so it's still a little confusing. Number 4 deals with a particular function, f of x equals 1/2 x cubed plus 2x minus 3. But because it's cubic, it still ends up being kind of abstract. Note that f of 2 does equal 5. If you plug in 2, you'll get 1/2 times 2 cubed is 8. 1/2 times 8 is 4. Plus 2 times 2 is plus another 4 is 8. Minus 3 is 5. Note that f is invertible. You'll see it passes the horizontal line test if you graph it. I will graph it on my calculator and we'll see that. Part A says find f inverse of 5 and f inverse prime of 5. What makes this difficult? What makes it difficult is because of the fact it's cubic, you can't actually find a formula for f inverse. That's still okay though, but you can use abstract ideas. Since f of 2 is 5, when the input of f is 2, the output is 5, and since f inverse exists, that means f inverse of 5 is 2. It's switching around the roles of what is input and what is output. F inverse of 5 is 2, since, by definition of the inverse function, f of 2 is 5. That's actually very easy if you know what you're doing. The second part of part A is also easy if you use the formula from number 3 that we just did. It's not so easy if you don't know that formula. What's the formula we just derived in the previous problem? F inverse prime of a number is 1 over f prime of f inverse of that same number. Okay, that's the abstract fact. We just found that f inverse of 5 is 2. This is 1 over f prime of 2. Oh, this is now not such a hard problem. I can easily find f prime. It's a cubic there. F prime of x. Differentiate this. You'll get 3/2 x squared plus 2. Use that now. You'll get 1 over, plug in 2 here, 3/2 times 2 squared plus 2. 2 squared is 4. 4 times 3/2, the 4 and the 2 would cancel. It would be 6. 6 plus 2 is 8. The answer is 1/8, okay, which is a decimal is 0.125. That's the answer for f inverse prime of 5. Part B says interpret this graphically. Okay, so let's use the technology here to do that. I'm not going to be able to graph the inverse function unless I found its formula. It's actually possible to find the formula. It's just a mess. I don't want to find it. I don't want to type it in here. So in my y equals screen, we'll just try to imagine the graph of the f inverse function. There's f of x. I also have y equals x. My window I picked is -8 to 8 in both directions, but we will want to do a zoom square to see the axes to be scaled the same. There's the original function. You can see it does pass the horizontal line test. No horizontal line goes through it more than once. And that means it's 1-to-1 function, which means it's got an inverse function. That is the reflection across y equals x, but it's only easy to do if you make the scales the same. So let me do a zoom square. Okay, when I first tried doing the zoom square, it was stalling on me for some reason. I redid it, it did it, it zoomed out. I don't like that so much. Let's maybe zoom in closer here. It's going -15.16 to +15.16. Let's cut that in half to about, what would it be, -7.58 or so. And we'll cut the y 1 in half as well. -7.58 to +7.58. And then -5 to 5 for y. And the point of interest will just barely be on the screen, actually. So there's the original function. Okay, so I can't actually plug the inverse function in here, but what would its graph look like? I'll try to just draw it without touching my calculator. It would be the reflection across the line y equals x. It would look about like this. And this point is the point 2, 5. The point of interest is the point on the inverse graph. That's 5, 2. 1, 2, 3, 4, 5, and then up to right around here, there'd be a point on the graph looking about like that. We've just verified it's symbolically that its slope would be 1/8, which seems reasonable. If I draw a line there, a tangent line, even though okay, this is a zoom box, so the scales are the same, it does seem reasonable that the slope of that could be close to 1/8. Certainly a positive number, very close to 0. Our last two problems are word problems that are practical situations, though we need the abstract formula. Let P equal f of t give the US population in millions in year t. Part A, what does the statement f of 2017 equal 327 tell you about the US population? All right, that's the year 2017, 327, that's in millions. That's telling you the population in the year 2017 was 327 million. The population in 2017 was 327 million. The US population. All right, that's pretty easy. Part B, find and interpret f inverse of 327. Okay, just like in the last problem, we're assuming f is invertible, which makes sense. The population does go up over time. It's an increasing function with a positive derivative, and it's going to be 1-to-1. We're just switching around the roles of what's the input and what's the output. Since f of 2017 is 327, that means f inverse of 327 is 2017. And the units would be the year. It's the year 2017. This is telling you if you were after what the year was when the population was 327, that's what this is telling you, so to speak. Is there a formula for f or f inverse? Well, there are probably approximate formulas, not necessarily an exact formula. Part C, what does the statement f prime of 2017 equal to 2.65 tell you about the population? Give units. It is a derivative. It is a rate of change. So it is going to be the rate of change of something. Let's use Leibniz notation to emphasize its meaning. F prime of 2017 is the derivative with respect to t of the population. It is dp dt, the rate of change of the population with respect to time, evaluated at time 2017, the year 2017, and it equals 2.65. Its units as a rate of change have to be the units for the dependent variable p per unit of the independent variable t. This would be million people per year. Million people per year. That's the units. Let me just interpret it by verbally saying how to interpret it as a rate of change. So that's saying in the year 2017, that's the rate of change of population in million people per year, meaning then as an estimate for the population in 2018, 1 year later, you would estimate that it would be 2.65 million people more, approximately. Maybe you'd round it to 2.7 or something, or maybe even 3. So if the population in 2017 was 327 million, you'd estimate the population 1 year later, change in t is 1, to be this much bigger. So it would be 329.65 million people. Again, you might want to round that, okay? That would be how to interpret that. I'm just doing it verbally here. Let's do the same kind of thing for part D. Evaluate and interpret this derivative, inverse function derivative, give units. You don't have to write the abstract formula for the derivative of the inverse function. F inverse prime of 327. We can, okay, it does say evaluated, so I guess we would need the formula. So that, by what we've been talking about in recent problems, is the same as 1 over the reciprocal of f prime, but not evaluated at 327, but instead f inverse of 327. So that would be 1 over f prime of what's f inverse of 327? It's the year 2017. And by part C, that's about 2.65, so this is approximately 1 over 2.65, or maybe we'll write an equal sign there, then we'll write an approximation at the end. 1 over 2.65 is about 0.38. Let's round it to 0.38. In Leibniz notation, This is not dp dt, but dt dp, evaluated at p equals 327. And its units would be the reciprocal of these units, years per million people. How should you interpret that? Let me just describe that verbally. It's a rate of change of time with respect to population when the population is 327. How could population be an independent variable and time be a dependent variable? Isn't time the ultimate independent variable? Yeah, but mathematically speaking, it doesn't really matter. We still could reverse the roles. Mathematically, it doesn't matter. So this is telling you, if the population goes up by about 1 million people, how much the year changes. It's taking about 38% of a year. When the population was 327, it's taking about 38% of a year for the population to get to 328. What's 38% of a year? Multiply this by 365 to get the number of days, about 137 days. I could have multiplied it by 12, say, to get the approximate number of months, about 4.5 months. So if you're thinking that the initial time when the population was 327 was at the very beginning of the year 2017, you have to go 4.5 months into the year, which is not April, it's actually May, because a complete 4 months would be the end of April. So about halfway through May is when the population went up by about 1 million people. Our last problem is once again a word problem. This graph that you see shows the number of motor vehicle registrations, F of t, in millions in the world, t years since 1960. So whereas in the previous problem, time was the actual year itself, here the time is since 1960s when you plug in these numbers here. The axis, though, is labeled with the actual year. T itself, we should probably relabel, would correspond again to years after 1960. This would be t equals 0, this would be t equals 10, 20, 30, 40, and 50. That'll help us not make a mistake. The goal is to estimate and interpret the following values: f of 40, f prime of 40, f inverse of 750, and f inverse prime of 750. Okay? We can do this pretty quickly, I think. F of 40, we're plugging in time 40, that's the year 2000, into f. We get the output to be the second coordinate of that point. Looks like it's pretty close to 750. Okay? This is approximately 750. Units would be, what are the units for f of t? This would be million vehicle registrations in the world. That's the answer. Part B, f prime of 40. We would have to interpret that as a slope. We don't have a graph of f prime. It's the slope of the tangent line here. We could try to draw a reasonable tangent line, estimate its slope, change in y over change in t in this case. If you let t increase by 5 from t equals 40 to t equals 45, say, how much does y, the number of registrations, increase? What's the length of that line segment? It's growing from about 750 to about, what would that be, 850 or so. It's growing by about 100. This is approximately 100 divided by 5 million registrations per year, 20 million registrations per year would be the value of that. Okay, that's just an estimate. Maybe you'd draw a slightly different tangent line and get a slightly different estimate. Part C, f inverse of 750. Go backwards. 700 is right there. I guess we were taking, they did want you to estimate f of 40 to be 750 here, I guess. This is not really a different situation. 750 is right there. Go backwards, the year back to the year 2000. F inverse of 750 is the year 2000, which is 40 years after 1960. Part C is the reflection, so to speak, of part A. Finally, part D, f inverse prime of 750. F inverse prime of 750, as we've seen, is the reciprocal 1 over f prime, but not of 750, instead of f inverse of 750. But that is 1 over f prime of 40, right? F inverse of 750 from part C is 40. And then from part B, f prime seemed to be about 20. F prime of 40 was about 20. So this would be 1/20th, or 0.05. Is that doing that right? Yeah, 1/20th is 0.05. Units would be years per million people. This is similar to the last problem. Or not million people, but million vehicle registration. So you would interpret this as a rate of change of time with respect to vehicle registrations in years per million vehicle registrations. It's telling you it's taking about 1/20th of a year to get the next million vehicle registrations. How much of a year is that? Let's do it with days. 365 divided by 20. It's about 18 days, so a little bit less than, or it's about 2.5 weeks, you might say, for another million vehicles to be registered. Thanks for watching.